And we're going to be talking about auditory masking today. As far as an agenda, we're going to touch briefly on the human hearing ability and what we mean by hearing threshold. And then we'll talk about two main types of masking, which will be spectral masking and temporal masking. So the human hearing threshold. If you look at this chart here, I've got level in decibels on the left-hand side and the frequency axis along the bottom here. And if I bring in this shape, this is the human hearing domain, a rough shape that approximates the human hearing ability. And so everything inside this blue area we can hear, and everything outside this blue area we cannot. It's either too quiet or up here it can get too loud. This is the pain threshold up here. We hear roughly between 20 hertz and 20 kilohertz, and everybody's a little bit different, but that's the nice round numbers that we use for the human hearing ability. So this line right here, we call the threshold of human hearing. Now there's a caveat to that, and that is what we would call the human hearing threshold in quiet. So that means there's no other sound present. It's just a listening experiment. How quiet can we play a sound across the frequency spectrum and still be able to have a listener hear it? Okay, so this is the minimum pressure in quiet. As we'll see, the presence of background noise or other spectral content will affect this line, and it will sort of warp and change this threshold. If you're curious, the 0 dB reference comes from the human hearing threshold in quiet at 1000 hertz. So 0 dB means you're measuring your dB reference value, and we as a scientific community chose the human hearing threshold at 1 kilohertz to set our dB reference. So that's where that value comes from, just a little bit of trivia. So first we're going to talk about spectral masking, and this is the presence of any other spectral content in the listening environment that changes that threshold of hearing. And we're going to talk about two main types: tones masked by broadband noise, and then we're going to look at tones masked by other tones. So if we look a little bit zoomed in on that last chart where I had the threshold of hearing in quiet, what we have learned is that if you introduce background broadband noise in the form of white noise, what it does is it modifies this threshold of hearing to these yellow dashed lines. And so depending on the level of that background white noise, the threshold of hearing gets raised. And the values at the extreme ends of the frequency spectrum aren't really modified too much. It's really in this middle section where our hearing threshold is changed or affected more drastically. And so these lines represent broadband white noise with an RMS level shown here in the center. So 33 dB all the way up to 93 dB. And this becomes now the bottom of this red trace. So we're going to spend our time listening to examples where we're looking at this 63 dB RMS background white noise. And so this line, the red line, will come down and kind of go across this dashed line and then go back up. So that's the new threshold of hearing given the presence of this background noise. Just a quick example, we have no other spectral content present. We have a 5 kilohertz tone played at 40 decibels. That's obviously above that red line. There's no other spectral content, and so we would say, yep, we're definitely going to hear that 5 kilohertz tone at 40 dB. So you see I have just a 5 kilohertz 40 dB sound. I'm going to play this for you. It should be very easy to hear this tone. So 5 kilohertz tone, clearly audible. If we were to introduce some background noise at an RMS level of 63 dB, that's going to raise that threshold of hearing to this yellow dash line, and 5 kilohertz tone at 40 dB is no longer above that threshold, and so we should not be able to hear it. So this is random plus 5 kilohertz at 40 dB. Okay, so we see the broadband noise and we see our spectral tone right there. So I'll play this guy for you. So depending on how you're listening to this, you may or may not have perceived that, but I cannot hear that tone. I'm in the room where it's being played, and it is completely masked. I cannot hear it at all. Now, if we were to move on and say increase that tone's amplitude and say, all right, let's play it a little bit louder and play it at 50 decibels, now we're above that yellow dashed line and we should once again be able to perceive that tone. So let's listen to that really quickly. We do hear that 50 decibel tone in there. So now let's talk about tones masked by other tones. If you've ever been to one of our sound quality seminars where we're talking about the sound quality metric of loudness, we've talked about Zwicker masking and sort of his discovery of this tonal masking phenomenon. Essentially, we're looking at the masking ability of a 1200 hertz tone. And so what Zwicker found is if you have this orange dashed line, this is the threshold of hearing. And he says, okay, well, if I've got a 4 kilohertz tone, as long as it crosses that threshold, I will be able to hear that tone. It's going to be audible. But what he found is that if he introduces a lower frequency, higher amplitude tone, in this case 110 dB at 1200 hertz, what happens is that hearing threshold gets distorted again by the presence of that high amplitude tone. And so now you see that orange dashed line actually is above that 4 kilohertz tone, and we will no longer hear it. Broadband background noise sort of affects all frequencies kind of equally. Tonal noises have this localized effect where they're affecting the frequencies higher or above the tonal masking tone frequency, more so than those below it. You see there is an effect below the masking tone, just not quite as significant as the effect above that frequency. And so this is a chart specific to 1200 hertz. This trend applies to all frequencies, and so Zwicker, in one of his psychoacoustics books, generalizes this into this chart here, where you have the level of the test tone here shown on the y-axis, and then this critical band value difference along the x-axis, I'm sorry. And then these different curves represent the level of the masking tone itself. Okay, so what are we talking about with this critical band value difference in bark? That has to do with this bark band, or the critical band rate, it's sometimes called. And essentially, this is a fancy version of the 1/3 octave spectrum. So we lump frequencies together in the 1/3 octave spectrum quite often because it's a pretty easy to use and semi-accurate model of how our brain lumps frequencies together. We don't hear in the narrow band, we hear in sort of the 3rd octave spectrum. It is more precise to say we actually hear in the critical band spectrum, and this is the definition of those critical bands. And so the bark scale goes from 1/2 all the way up to 23.5, and these are the sort of the name of the bark band. So if we have two tones and we want to use Zwicker's chart here, we first have to convert the frequencies we're talking about into their equivalent bark band. Essentially, we just look at the two frequencies we're talking about, convert them to bark bands, and then look at the difference between the masking tone and the tone we want to know whether it's going to be masked or not. We look at the difference between those two, find out where we are on the x-axis, and essentially anything below these curves will be masked, anything above will not be masked. So these are sort of the threshold of hearing lines for this family of different masking tone levels. Example number 1. We're going to say our masking tone is 1000 hertz, and that's going to be 70 dB. So we're going to be looking at this curve right here. This is the threshold curve for a masking tone of 70 dB. And the tone we want to assess, whether it will be masked or not, will be 1370 hertz at 35 dB. So this is what we're going to look at on the y-axis, okay? And so if I throw these two frequencies, so masking's 1000, the tone we're interested in is 1370. So I just made this simple little Excel sheet. Masking frequency is 1000. This is 1370. Our delta bark is -2.1. Okay, so our delta Z is -2. So we have this line here, and then our tone that we want to assess is 35 dB. So we look at this level right here, and that ends up bringing us to this yellow dot. And our masking tone is this 70 decibel curve. So we see this yellow dot is below this curve, and so that tells us that our tone will be masked. So 1370 at 35 dB will be masked by 1000 hertz at 70 dB. Here is the masking tone. Okay, good old-fashioned 1000 hertz. This is our tone we want to assess. This is 1370 hertz at 35 dB. Okay, and I'm going to put these two together. Let's see, this guy will be just the masking tone. This guy will be both. It'll make it a little bit more obvious for you. I'll keep flipping back and forth and see if you can hear this tone. So let's see what happens with some different example frequencies. So now we're going to talk about a masking tone at 770 hertz at a level of 45 decibels, and a tone we want to assess at 2000 hertz at a level of 40 decibels. The delta bark is -6, so we're way out here now. And we see we're at the -6, and our tone we want to assess is 40 dB, so it puts us out here, but our masking curve is really somewhere in between the 40 and the 50 here, right? So the difference in frequency between the tone we want to assess and our masking tone is large enough that the effect of the masking tone is long gone. Okay, so one of the things you need to remember about tonal masking is the farther apart in frequency the test tone and the masking tone are, the less likely the masking tone will mask that test tone. This is not going to be masked, but I'll play it for you just to show you. Okay, so that's just the masking tone. Here's with both. Just the masker and the test tone. Not masked at all because they're separated in frequency, and so quite easy to discern those two. So let's keep that frequency difference. So I'm not going to change anything about the frequencies of the tones. I'm just going to change some of the amplitudes here. So I'm going to increase the amplitude of the masker all the way up to 70, and I will have the test tone at 30 decibels, okay? So once again, we're at -6 in the bark scale difference, and then our level is 30 decibels. Our masker is now this 70 decibel curve, so we see we are above that, so we should not be masked. Let's see if that is indeed our experience. So let's again try to make this a little bit more interesting. And now we'll have 15 dB for our test tone. Okay, so we're going to be way out here in the frequency difference, but our test tone is now only going to be 15 decibels. So now you see we just tuck underneath that masking curve. So this one should disappear and we should not hear two distinct tones. Let's again verify that. Masker with the tone. So I can just barely hear that, as it might be suggested by how close that intersection is to the masking curve. I've been listening to these tones quite a bit, and so my brain is very tuned into that test tone. That training is part of increasing our ability to perceive something. If we know exactly where to look, or listen rather, it's sometimes we can extend that hearing ability just a little tiny bit. And so again, depending on where I hold my head, listening to my loudspeakers, I can just barely hear that tone. So that's tonal masking. We can use this chart to kind of decide whether or not maybe we have a couple tones being produced by our machine and we know one's lower in frequency and maybe louder. Do we need to worry about that higher frequency one? charts like this can give us an advanced idea, and then ultimately we can test that out by making some measurements and doing some jury testing. So temporal masking, this is a little bit different effect, but this has to do with the time response of the human hearing mechanism with our eardrum and the cochlea and all that. Those are not instantaneously responding devices, and so we have some temporal masking effects as well. In the center here, we're going to have, for this example, a masking tone, a broadband noise that's 60 decibels will come in and start right here at this time equals 0. It will continue for 200 milliseconds and then shut off. And you see we've got some different time scales here, and that's because there's both a post-masking effect, which means after this masking noise shuts off, our hearing ability takes some amount of time to return to our threshold and quiet ability. There's even a pre-masking effect, which means any noises that happen very close in time to the masking sound, even though it happens before the masker has even occurred, our brain will not hear that sound. We do not perceive it. So this new sort of maroon curve is the threshold of hearing due to this transient masking noise shown in gray. Sound quality metrics, at least time varying loudness, actually perceives this effect. So it's got this temporal masking effect baked right into the algorithm. And so you see three different signals here. This high amplitude masking noise shown here is far enough away in terms of time from these low amplitude short bursts that we see the lower amplitude short bursts appear in our time varying loudness. So you hear a small blip, and then you see the masker, and then after a few seconds or a second or so, you hear another small blip, and we perceive all three of these events. And time varying loudness shows us that in the time varying loudness plot. With the pre-masker, you see this small sound come right before, a short period of time before the masker, and you notice this time varying loudness shows you no little blip here. It's as if it didn't even happen. Okay, and this is going to match our perception. Same with post-masking. You see this one happens a little bit even further. You can wait a little bit longer, but still no effect here. These are those same plots I just showed you in the PowerPoint. This happens far enough in advance before the masking and longer enough after the masking has disappeared that we perceive both of those. Pre-masking, you see in that PowerPoint, this doesn't have any effect earlier than 50 milliseconds before the masking appears. And so you see this is 50 milliseconds between my double X cursors here, and you see that small amplitude burst happens right before the masker, and so that threshold has come up to the level of the masking by now, and we will not perceive that low amplitude short burst. And then similarly for the post-masker, there can be effects all the way out here to 200 milliseconds after the masking sound has disappeared, but most significantly, again, 50 milliseconds after the end of that sound. So if I look at time post-mask, this is 0.08 of a second or 8 milliseconds after the end of the sound. Here's that 50 milliseconds, and so you see this is still close enough that it's being masked by this sound here. And we see that in this time varying loudness curve. So the red is there's no masker or they're far enough away from the masking event, and so you see a small, the low amplitude sound happen, then the loud sound, and then the smaller amplitude sound. And then the pre-masker and the post-masker are overlaid, and you see no response from the time varying loudness metric until the masker, and then nothing afterward.
And I'll play these for you now. And keep in mind that the second and third traces I'll play for you aren't going to be very much to listen to because these little sounds will be masked as the time varying loudness shows us. But in this first trace, see if you can detect these tiny little tap noises that come before and after the masker. Again, not much to hear in that second and third trace, as time varying loudness kind of clued us in on. But just to show you that, an FFT won't be fooled in the same way our brain is, these are those three same recordings. First, no masking, where you can see the small tap noise. It's a broadband noise that we see across the frequency band, and we see it tap, and then a louder, higher amplitude masking noise, and then a small tap afterward. So we perceive this one. Pre-masking, you see the masking noise here. If I zoom in real closely, you see the FFT captures this event no problem. I used a very fine time step here of 1/100th of a second and 100 hertz resolution. And you can actually see this period of no sound in between the short low amplitude sound and the masking noise. So the FFT, no problem in picking this up. For the pre-masker, same thing for the post-masker. If I zoom in, you see this masking noise and then the small tap afterward. So it's really just a biological side effect of the way our hearing mechanism works, that there is this masking effect. Something like a microphone or an FFT of that microphone recording will not be fooled in the same way our brain will.
Just to sort of summarize, spectral masking, this is a masking effect due to the presence of other spectral content. This spectral content can be broadband, like white noise, or it can be tonal noise or individual frequencies. If it is broadband noise, this has an effect of raising the threshold of hearing across all frequencies, not necessarily equally, but all frequencies will be affected, whereas tonal masking, that is not the case. Frequencies above the masking tone will be affected more than those below the masking tone. But in both cases, the louder the masking sound, either the broadband noise or the tone, the greater the masking effect, or the more frequencies it will mask in the case of a tone. And then temporal masking is the masking of sound due to the time delay response of the human auditory system. So our hearing mechanism takes a little bit of time to get going, and it has some after effects even after the sound has stopped. And so those two effects will tend to make things that happen very close in time to the masking noise sort of disappear from our perception. And it can happen both before and after a masking sound.